look at orthogonal sets and orthogonal projections. So we've got 4 vectors here, u1 to u3 and x. So I want to show that u1, u2, and u3 form what's called an orthogonal basis. So we already know what both of those words mean separately. Orthogonal, perpendicular, right? Basis, a linearly independent spanning set for R3. So linearly independent and spans R3. And orthogonal means that any set of 2 are orthogonal to each other. So orthogonal, all orthogonal to each other. And basis is a linearly independent set that spans R3. So to show they're orthogonal to each other, we just dot product u1 dot u2. So that would be -1 plus 0 plus 1, which is 0. Check. Right. u1 dot u3. That's 1 times 2 is 2. Plus 0 plus -2 is 0. Check. And then the only other set is u2 dot u3, which would be -2 plus 4 minus 2, which is 0. Check. So it's an orthogonal set because every element is orthogonal to every other element. Now to just show that it's a basis, I have to show that those 3 vectors are linearly independent and that they span R3. How do I show that? Row reduce the matrix, and I'm looking to have a pivot in every column and a pivot in every row. So it's going to row reduce to the identity if this is, in fact, a basis. And it does. It row reduces to 1, 0, 0, 0, 1, 0, 0, 0, 1. So it is linearly independent. It spans R3. So it is a basis. If in addition to using the word orthogonal and basis, if instead of orthogonal I said that u1, u2, and u3 are going to be normalized so that they all have length 1, that's called an orthonormal basis. So that's an orthogonal basis where all the vectors have length 1. All right, so I want to express the vector x that I gave you as a linear combination of the u's. So I want to figure out what weights do I put on the u's to build the x, right? So I've got c1, u1 plus c2, u2 plus c3, u3. I want to express x as a linear combination of the u's. So the question is, what are c1, c2, and c3? So this is a question I could have asked you in like the second week of classes, right? You basically just set up a matrix augmented with the x and row reduce. So this is going to be 1, 0, 1. That's u1. u2 is -1, 4, 1. u3 is 2, 1, -2. Augment with your x, which is 8, -4, -3. And row reduce, and you'll get your c's, your vector of unknowns. So this row reduces to 1, 0, 0, 0, 1, 0, 0, 0, 1, 5 halves, -3 halves, 2. So I get C1 is 5 halves, right? This is your C1 column, your C2 column, your C3 column. So C2 is -3 halves, and C3 is 2. So that's the old-fashioned way. Now, because I have an orthogonal basis, I have a very special set for U1, U2, and U3. I can use these other formulas, these other fancy formulas that are based on the fact that U1, U2, and U3 are an orthogonal basis for R3. So my special formula is, if I want to know my weights, C1, C2, C3, there's a formula for C sub j for any particular weight that you're looking for. It is y, or in our case, x. It is x dotted with u sub j over u sub j dotted with u sub j. And that'll give you the weight, right? So if I want C1, I would do x dotted with u1 over u1 dot u1. So let's go ahead and we'll calculate C1 here. So my x is 8, -4, -3, dot with u1, which is 101, over u1 dotted with u1. So that's 101 dotted with 101. So that's 8 minus 3 over 1 plus 1, which is 5 halves, which is exactly what we got in our old-fashioned method. So again, this only works because we have an orthogonal basis. You can't use this anytime you want, but when you know your basis is, your set is an orthogonal basis, you can go ahead and use your special formula. So C2 would be x dotted with u2 over u2 dot u2. U2 is -141. So you can see this is why I was making you do all kinds of computations in the activities before, where you were doing dot products over dot products to practice doing this. So this comes out to -8 minus 16 minus 3 over 1 plus 16 plus 1, which is -3 halves. And then I won't go through C3. It comes out to 2. Big surprise. All right. I want to compute the orthogonal projection of y onto the line that goes through the vector u and the origin. And then we're going to write y as the sum of 2 orthogonal vectors, one in the span of u and one orthogonal to u. And that sounds like complicated, but I'm going to draw a picture of what it's asking, and then we're going to estimate from the picture the answer, and then we'll do it with formulas. So first, I'm going to plot the point 1, 7, or I'm going to draw the vector 1, 7, and the line through -4, 2 in the origin. So I should really add some axes to the notes here. All right. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. One, 7. So that's y. And I'm just gonna draw it as a point and not a vector for the moment. And then the line through -4, 2 in the origin. So I've got 1, 2, 3, 4, 2. Here's my line. And any vector on this line is in the span of u, right? Any multiple of -4, 2 will be on that line. So what they're asking me to do is to write y as the sum of 2 vectors. They're going to be orthogonal to each other, one of which is in the span of u, and the other is perpendicular to u. So it's called the orthogonal projection because I'm going to project y onto u by drawing a perpendicular line. So I'm going to go from y, draw a perpendicular line to u. Okay. And that point right there is in the span of u. That point is on the line, it's in the span of u. That's one of the vectors I'm looking for. One of the vectors in the span of u. The other orthogonal to u, that's the pink vector I just drew. Okay, so this vector here, that's one of the ones I'm looking for, and we're going to call that y hat. It's in the span of U. And then the pink one, from the pink point up to Y, we're going to call that vector Z, and it's orthogonal to span of U. So I'm looking for the green vector and the pink vector. All right, so my green vector, my estimate here, based on the picture I drew, looks like -2, 1. And my estimate for Z, so we typically measure vectors from the origin. So you can either like picture sliding this to the origin, or you want to go over and up, break it down into its horizontal and vertical components. So this vector Z looks like it's 3, 6, over 3, up 6. Everybody see that? Okay, are those two vectors orthogonal? Y hat and Z? Yeah, so that's good because they wanted me to come up with 2 orthogonal vectors. They are orthogonal. -2 times 3 plus 1 times 6 is 0. If I add them together, do I get my original vector 1, 7? Yes, so I think I found them. This is the answer to the question, right? My original vector y is equal to y hat, -2, 1, plus z, 3, 6. So I wrote y as the sum of 2 vectors that are orthogonal to each other. One of them is in the span of U because -2, 1 was on the line, and the other one's orthogonal to U. That's the pink perpendicular drops down to the line. So you can do it visually if everything is like nice and integer-y, right? And you draw a really good picture. Isn't it what? Okay. Or we have formulas that will calculate y hat and z. Okay, so y hat, we already know that y hat, the orthogonal projection of y onto the line containing u, is -2, 1. The formula that gets us there is going to be y dot u over u dot u times u. These are all vectors. Okay, so y is 1, 7. So I have 1, 7 dotted with u, which is -4, 2, over -4, 2, dotted with -4, 2. And that's a scalar. When I do all that out, it's a scalar, and I'm going to multiply that scalar times the vector u, -4, 2. So when I dot these, I get -4 plus 14 is 10. And then 16 plus 4 is 20. So I have 10 over 20 times -4, 2, which is a half of -4, 2, or -2, 1. So there's my y hat. Same thing I got just by drawing the picture. And then z, you can just calculate by doing y minus y hat. So y is 1, 7. Y hat is -2, 1. So z is 3, 6. So I found the 2 vectors using formulas. Then the picture? Yeah, it's definitely easier. I just wanted you to see what we were doing, what we were finding. So finally, just to answer their question, they said to write y as the sum of 2 orthogonal vectors, y hat and z, -2, 1, 3, 6. And then you should identify this one is in the span of U, and this one is orthogonal to U. And they're orthogonal to each other.